Hello, calculus students. Today we're looking at lesson 8, which is horizontal asymptotes and composite functions. So we are going to be able to evaluate limits approaching infinity and relate them to horizontal asymptotes. Now, I know one of the previous practice pages had some infinity problems on there. If they didn't get whited out appropriately, you may or may not have tried to look those up, but today we're going to talk about how to actually solve them. So for the warm-up, given the following function, find the horizontal asymptote of the graph. You actually learned how to do this in pre-calculus. This is an x, by the way, f of x. So f of x equals 3x squared minus 6x over 2x squared. In pre-calc, you had rules about the exponents, and where the power was higher in the numerator, you had a slant asymptote or no asymptote. If the powers were the same, it was the ratio of those leading coefficients. And if the power in the denominator was greater, then your horizontal asymptote was 0. So in this case, we're looking at x squared and x squared. Those are the two powers we're looking at. The numerator has a 3 and the denominator has a 2. So your horizontal asymptote is y equals 3 over 2. Now, a horizontal asymptote is a line. I really want to see you write this as the equation of a line. Y equals 3 over 2 is a horizontal line. 3 over 2 is just a value. You want to see y equals 3 over 2. And so a couple of rules. Let's try to combine what we did in pre-calculus with some of these calculus ideas. If the highest power of x appears in the denominator, there's a horizontal asymptote at y equals 0. This is how you learned it in pre-calculus. It's very important to remember when dealing with limits that 1 over infinity is equal to 0. If the highest power of x appears in the numerator, there is no asymptote, but there could be, there doesn't have to be, there could be a slant asymptote. This means that the limits does not exist. Where's infinity? Probably infinity is the better answer on that one. It could be negative infinity as well. Remember I said if it was multiple choice on the AP exam, you'll have either does not exist or infinity as a choice. You won't have both. So both of those notations are acceptable. And if the highest power of x is the same in both the numerator and denominator, there is a horizontal asymptote at y equals, and I know in your pre-calc you use p over q, but it's the ratio of the coefficients. You have to check the sign at the limit to know if you're dealing with positive or negative. So I have never actually taught pre-calculus. I've taught all the other classes, but not pre-calc. So I look at this with the limits, and I look at the limits as we go to infinity. And what you want to ask yourself is, if you put infinity in place of x, does it really matter if you subtract a 1? The answer is no. Infinity minus 1 is still infinity. And if I have infinity cubed, and this is infinity to the first, that infinity to the first doesn't matter. The infinity cubed is more important. So you don't need these other values. And what you can do is ignore them. So you can ignore these, and you can ignore these. So you keep the highest power in both the numerator and denominator. Now, you could be looking at this problem going, hey, I know what the answer is, it's 4/5. That's what we did in pre-calc. That's totally fine. I have a tendency to write these out. So I have 4x cubed over 5x cubed, and that other stuff doesn't matter, remember? Those other terms. Then I do a little bit of algebra. What can I cancel out? Well, I can cancel out the x cubes. Those don't matter. So I am left with 4/5. That's kind of how I think of it. But again, you may have gotten 4/5 before you even looked at the problem. For example 2, this time we're substituting negative infinity. So you want to keep the highest power, but just be smart about it. They don't have to be written in standard form with that highest power first. So I'm looking through the numerator. I see an x cubed to the right. So x squared is insignificant. 5x is insignificant. 6 is insignificant. In the denominator, negative 2 doesn't matter, and nor does the 5. So if we rewrite this, it's the limit as x approaches negative infinity of negative 4x cubed over 7x squared. So I tell my students, be a good algebra student, simplify the calculus that you can. So we have the limit as x approach, or the algebra, I just said calculus, the algebra. So this is negative 4x over 7, because those x's will cancel out. Now if I put a negative infinity in place of the x, it's not that it's a number that you can substitute, but you want to watch the signs. So negative 4 times negative infinity would be positive infinity divided by 7 is still positive infinity. So that's the real answer. This is kind of thinking in your head, this step, but your answer is positive infinity. That x power, the exponent in the numerator is greater. Over here, example 3. Again, what is insignificant? The 1 doesn't matter, and the 4 doesn't matter. We have the limit as x approaches infinity of negative x squared over x squared. So be a good algebra student, simplify as much as you can. Those x squareds cancel out. So we have the limit as x approaches infinity of negative 1. So my answer is negative 1. Again, the rules from pre-calculus and the rules listed above on your notes say that if the powers are the same as the ratio of the coefficients, so negative 1 over 1 is negative 1. It's however you think of it. Example 4. If we're substituting infinity in the numerator, 6x is insignificant, negative 3 is insignificant, and the denominator 7 is insignificant. So this is essentially the limit as x approaches negative infinity of 2x squared over negative 2x cubed. If I simplify these algebraically, those x's cancel out. And the 2's cancel out actually. So I've got a 1 over negative 1x. If I place infinity in place of x, I've got negative 1, no, excuse me, positive 1, negative infinity. Again, this is the part you're just thinking in your brain. You want to check the signs. So in the denominator, negative 1 times negative infinity would be positive infinity. So I'm left with 1 over infinity. That's not a number, but it's a fraction so small, it's 0. And if we were in class together, I'd write this on the board. I'd say, hey, what's a small fraction? 1/2 is pretty small. Yep. 1/4 is even smaller. 1/10 is even smaller. 1 over 1,000 is even smaller. 1 over 1,000,000 is really small. And then sometimes the lottery's got a really big jackpot. So I say, what are your odds of winning, you know, the Powerball? How many tickets were sold? And it's millions and millions of tickets that are sold. That fraction is so tiny that if we do 1 over infinity, it's so small we consider it 0. 1 over infinity is 0. So there we go. There's our 0. All right, I've got another idea for you, and that is limits of compositions. So sometimes we can figure out what limits are without being given the exact function. So for example 5, I have the limit as x approaches negative 1 of f of x is 2. The limit as x approaches 1 of f of x is 4. And the limit as x approaches 1 of g of x is 6. So given the above values of f and g, what is the limit of this crazy composition going on here? So let's check this out. All right, so we are looking at the composition of functions here, and a lot of these problems have to do with the notation. So what we're going to do is I'm going to take a minute and split this apart a little bit so it's not so overwhelming. Remember, one of those limit properties is you can find the limit of each piece and add them together. So this is, my pencil's not connected anymore. Oh, it's just a little slow. Never mind, it's there. So this is, oh goodness, the limit as x approaches 1 of f of negative x plus the limit as x approaches 1 of g of x over 2. Something like this. So now you can look at each piece individually. So for that first piece, the first term, we'll put 1 in for that x. So this becomes f of negative 1. Now, when I look up above, what's the limit as x approaches 1? There we go. Sorry, my pencil's a little slow, I'm distracted. So we're looking for that limit as x approaches 1 gives us f of negative 1 when we substitute it in. So you want to look up above. We're dealing with the f of x. We're going to look at this piece. X approaches negative 1 of f of x is equal to 2. So that's actually all of this here. So this first piece is equal to a negative 2. Now, all right, I need to reset this here. All right, we had to reset there. So the first piece is equal to 2. Now in that second piece, that second term, same thing, you'll put the 1 in for the x. So this becomes the limit as x approaches 1 of g of x. So you're really putting in g of 1 over 2. Well, that g of 1 piece is for the the third piece that's defined up here. So this is 6 over 2. So I've got 2 plus 3 gives me 5. All right, very good. Now, example 6. Given the following graph, what is the limit as x approaches 6 of f of x? Now, this is a composition of function. There's also a typo here. So I would like you to, let's switch colors. Not 6, but make this 4. Make that a 4 for me, okay? So we are going to find the limit as x approaches 4 of f of x. This is what it should be. So we're going to put the 4 on the very inside. You start in here. So this is the limit as x approaches 4, or this is equivalent to f of 4. So once you put that 4 on the inside, you're going to come over to your graph and evaluate it. So here's 4, and you come up here and draw yourself a dot. So f of x or f of 4, you're really looking for the y value, which is 1. So this inside gets replaced with a 1. So we've got the limit as x approaches 4. Now this becomes f of 1. So when I look at the graph this time, over here is 1, down to the curve where it connects, the result is -1. So you can get those values from a table that's given to you. You can get them from a graph. Example 7, the table below gives selected values and limits for the functions f, g, and h. So kind of the same idea of what we have going on above. This one's not too bad. You can substitute what you need. I won't rewrite everything this time. Let's just kind of substitute everything in. So h of 5 is given here, which is 5. F of x, which is really going to be f of 5. All right, so we've used the 5. Now, f of x, and again, we're dealing with the limit piece, which is over here on the right-hand side of the table, not the left-hand side of the table. So f of 5, the limit as x approaches 5, we're dealing with f of x up here is our 6, plus 2 times g of x, the limit as x approaches 5 of g of x is over here is a -1. And we're going to close up those parentheses. Now, the limit piece, it's a little tricky to see all those parentheses, but the limit piece is here. Minus h of 5 at the end, we're not dealing with the limit over here at the end, you're just dealing with the function. So you're going to grab that off the table and get a 3. So we want to go back and evaluate this, keep going. So order of operations was my algebra lesson today. So 2 times -1 is -2. This becomes a 4. Here's my 5 on the outside. This is a 20. I'm going to switch colors back. -3, -3. 20 minus 3 is 17. So just be careful if you're looking at the actual function value or the limit value, because remember, those can be 2 different things. In a discontinuous function, those are 2 different things. In a continuous function, they would be the same. So there you go, folks. We're looking at horizontal asymptotes and composition of functions with limits. So keep the questions coming, keep asking me, keep asking Mrs. Oakes, keep working through those practice problems. I know that you're not getting every single assignment checked. That's coming through the warm up the next day where we're really testing for understanding. Do you understand what's going on? But you still want to do those practice problems. You still want to do them. This isn't something that you can just wake up for and cram the morning of the test. So good luck and keep the questions coming.